Example 4. Determine the domain and range of the graph below. In the graph above, the input quantity along the horizontal axis appears to be year, which we could notate by the variable y. The output is thousands of barrels of oil per day, which we might notate with the variable b for barrels. The graph would likely continue to the left and right beyond what is shown, but based on the portion of the graph that is shown to us, we can determine the domain is 1975 less than or equal to y, and y is less than or equal to 2008. And the range is approximately 180 less than or equal to b, and b is less than or equal to 2010. Remember, in the previous example, x and y are not always the input and output variables. Using descriptive variables is an important tool to remembering the context of the problem. Domains and range of the toolkit functions. We will now return to our set of toolkit functions to note the domain and range of each. Constant function, f of x equals c. The domain here is not restricted. X can be anything. When this is the case, we say the domain is all real numbers. The outputs are limited to the constant value of the function. Identity function, f of x equals x. Quadratic function, cubic function, reciprocal, reciprocal squared, cube root, square root, absolute value function. Find the domain of each function. Example 5. A. F of x equals 2 multiplied by the square root of x plus 4. B. G of x equals 3 divided by 6 minus 3x. A. Since we cannot take the square root of a negative number, we need the inside of the square root to be non-negative. X plus 4 is greater than or equal to 0 when x is greater than or equal to negative 4. The domain of f of x is close parentheses, negative 4 to infinity, open parentheses. B. We cannot divide by 0, so we need the denominator to be non-zero. 6 minus 3x equals 0 when x equals 2, so we must exclude 2 from the domain. The domain of g of x is open parentheses, negative infinity to 2, open parentheses, union, open parentheses, 2 to infinity, open parentheses. Piecewise functions. In the toolkit functions, we introduce the absolute value function, f of x equals absolute value of x. With the domain of all real numbers and a range of values greater than or equal to 0, the absolute value can be defined as the magnitude or modulus of a number, a real number, value regardless of sign, the size of the number, or the distance from 0 on the number line. All of these definitions require the output to be greater than or equal to 0. If we input 0 or a positive value, the output is unchanged. F of x equals x if x is greater than or equal to 0. If we input a negative value, the sign must change from negative to positive. F of x equals negative x if x is less than 0, since multiplying a negative value by negative 1 makes it positive. Since this requires two different processes, or pieces, the absolute value function is often called the most basic piecewise defined function. Piecewise function. A piecewise function is a function in which the formula used depends upon the domain the input lies in. We notate this idea like f of x equals piecewise formula 1 if domain to use formula 1, formula 2 if domain to use formula 2, formula 3 if domain to use formula 3. Example 6. A museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for 10 or more people in the group. Set up a function relating the number of people n to the cost c. To set up this function, two different formulas would be needed. C equals 5n would work for n values under 10, and C equals 50 would work for values of n 10 or greater. Notating this, C of n equals piecewise 5n if 0 is less than n and n is less than 10, 50 if n is greater than or equal to 10. Example 7. A cell phone company uses the function below to determine the cost C in dollars for G gigabytes of data transfer. C of G equals piecewise 25 if 0 is less than G less than 2, 25 plus 10 multiplied by G minus 2 if G is greater than or equal to 2. Find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes of data. To find the cost of using 1.5 gigabytes of data, C of 1.5, we first look to see which piece of domain our input falls in. Since 1.5 is less than 2, we use the first formula giving C of 1.5 equals $25. To find the cost of using 4 gigabytes of data, C of 4, we see that our input of 4 is greater than 2, so we'll use the second formula. C of 4 equals 25 plus 10 of 4 minus 2, which equals $45. Example 8. Sketch a graph of the function f of x equals piecewise x squared if x is less than or equal to 1, 3 if 1 is less than x and x is less than or equal to 2, 6 minus x if x is greater than 2. The first two component functions are from our library of toolkit functions, so we know their shapes. We can imagine graphing each function, then limiting the graph to the indicated domain. At the endpoints of the domain, we put open circles to indicate where the endpoint is not included due to a strictly less than inequality, and a closed circle where the endpoint is included due to a less than or equal to inequality. For the third function, you should recognize this as a linear equation from your previous coursework. If you remember how to graph a line using slope and intercept, you can do that. Otherwise, we could calculate a couple values, plot points, and connect them with a line. At x equals 2, f of 2 equals 6 minus 2 equals 4. We place an open circle here. At x equals 3, f of 3 equals 6 minus 3 equals 3. Connect these points with a line. Now that we have each piece individually, we combine them onto the same graph.